going to talk about the quantum mechanic model. These notes will really focus more on writing quantum electron configurations, but I will give a little bit of a background on the actual quantum mechanic model that dictates how we write these. Quantum mechanic model was based on Erwin Schrödinger's mathematical equations in the 1920s. And what he was basically trying to do was he was concerning himself with where we might find electrons. As we've talked about, because electrons move around a lot, you can't really know a whole lot about them. Once you figure out where they are, they've probably moved. But he is pretty good at, finding the likelihood that you might be near one. So we have some different quantum numbers. We're going to focus on what's called the principal quantum number and the orbital designation number, or the sublevel, if you will. When we put these numbers together, they really give us an address for where an electron might be. There's also something called magnetic quantum number and the spin quantum number. These are not quite as important to us at this level, although we will, when we draw diagrams, we will be careful with the spin by making our electrons face different ways. So most of our description will be in terms of N and L, or principal and orbital designation. Principal quantum number is exactly what we talked about in the Bohr model. It just tells you the PEL. So if you're talking about the second PEL, which holds 8 electrons, that's N equals 2, for example. Sodium is on row 3 of the periodic table, so its highest principal energy level is the third energy level. That's N equals 3. Within a principal energy level, there are these little kind of more organized orbitals. I like to think about them as the little thing inside of your silverware drawer. If I went to your house and wanted a fork, I would open the silverware drawer. Within the silverware drawer, most of you probably have one of those little plastic caddies that separates forks from spoons from knives, or some sort of, divider like that. The little dividers are kind of like these orbitals. They're within the principal energy level, and they're just a slightly more detailed way of looking at location. So the atomic orbital, which we were just talking about, is a little slightly more detailed way of looking at location within that principal energy level. We designate them by letter, S, P, D, or F, and they have some kind of weird shapes. In general, higher energy levels have more room for electrons in them, and these do tend to be further away from the nucleus. So if we look at this diagram right here, this is our first principal energy level. It's very low energy. It's our lowest energy orbital. That's a very small energy level. It doesn't fit a whole lot. But once we get up to like the third principal energy level, we have a much larger energy level here, and we have more sublevels. So each of those little boxes are places that we can put electrons. As we get farther away from the nucleus, which is way down here, we're going up in increasing energy, and we're also getting more space to put electrons. Now, in terms of energy, some of these don't go in an expected order. You can very clearly say 1s is the very bottom here. When you get to the second principal energy level with its 2 separate orbitals, it's clearly above the first principal energy level and below the third. But we do run into this weird point where the 3d is actually higher than the 4s. 4s orbital has less energy than 3d. The 3d actually fits more electrons in it, so it kind of works with that model too. So this is kind of a weird little thing. We do have a way of dealing with this. We're going to draw a little diagram that'll help us to predict when that's going to occur. So orbitals have some weird shapes. The s orbitals are spherical, which isn't too weird. So they look pretty predictable. What's kind of interesting about this picture right here is if you imagine each one of these is a bunch of pictures of one electron. So if you think about those sports cameras that take a whole bunch of pictures over and over and over again, if we used one of those and took a picture of an electron as it moved all over the place within an orbital, and then we were able to lay those pictures over each other, the picture that we get would show us that general shape of where we're likely to find an electron. For the s orbital, it would give us the spherical shape. P orbitals are kind of more of a dumbbell shape. D orbitals have kind of a dumbbell shape as well, but they have 5 different shapes because they're in so many different dimensions, so this picture gets kind of complicated, but we're not so much worried about the shapes at this point, just figuring out, hey, what are our principal energy levels and what are our orbitals. So as we write these configurations, we're going to follow a couple of rules. One of those rules is called the Aufbau principle. And this says electrons enter orbitals of lowest energy first. This just means when you're filling up one of these diagrams, you put electrons in the lowest energy orbital first. We do the same thing with Bohr. And you don't need to worry about the details, the name for this. Just follow the rule. Pauli exclusion principle says that no two electrons can have the exact same quantum number. This just means that two electrons can't be in the exact same place at the exact same time, just like people. Hund's rule says that when electrons are occupying equivocal orbitals in terms of their energy, they must not pair together until we've filled up the whole orbital. So what I mean by this is, I'm going to put 5 electrons into this d orbital. Now, when I draw electrons, I actually show them as little arrows to represent something called spin. I mentioned we're not going to really be super concerned with spin, but we will make sure that when we draw our electrons, we show them with the proper spin. Proper spin means if they're paired, they're facing the opposite way. So if I start with my 1 electron here, okay, and you can show this as like I do this way, you can show a full arrow, but it kind of gets old. If I have to put in my other 5 electrons now, it's just like when you get on a bus full of strangers, rather than sit with somebody, you're going to try to get an empty seat. So this first electron is here. My second electron will go here. 3, 4, 5. So rather than pairing electrons like that, I filled up each orbital, or put 1 electron, I shouldn't say filled up because each one can hold 2. I put 1 electron in each one. Now if I had 8 electrons that I had to place into the same orbital, my first 5 would not pair, and my last 3 have to pair, and they have to face in the opposite direction. That's taking care of that thing we call spin, that we're not going to worry about the details about, but we're going to show it properly by making sure that our electrons are opposite when they pair. So the first thing we're going to do to write a quantum configuration is find the atom on the periodic table and determine how many electrons it has. So to start with a small atom, we're going to start with sodium. Sodium has 11 electrons. Next thing I'm going to do is I'm going to draw something called the Christmas tree diagram. The Christmas tree diagram is to help us deal with this. Where are things unpredictable? Now in terms of the Christmas tree diagram, once you've drawn one of these somewhere, you can pretty much access the same one a whole bunch, but it's nice to get a little practice drawing it for things like tests and quizzes. But you can answer a whole bunch of problems using the same one. So this tells us we're going to start here. This is our lowest energy spot. Our first electrons go in the 1s. Then next we go to the 2s. Then the 2p, then the 3s. Now where it gets weird is right here. So next we go to the 3p. This actually tells us to go on to the 4s before the 3d. So it's important to practice drawing a Christmas tree. So I'm going to have you take a moment to do that. And you really only need to go up to level 4. So what I do is I start by going 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4, f. So I'm going to start up here, and then I kind of like to say, okay, and then I'm going to go next to the 2s, then swoop, 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 then 2p3s, then back up to the top, and back up to the top, and etc. This will take you up as high as you really need to go. If you can go up to about the 4p, we don't do atoms a whole lot bigger than that. So next thing we're going to do, and we're going to actually, I'm going to kind of show you these. I'll often give you a little diagram to fill out. The diagram that's on the left, it's got a little bit more color to it, and you don't need to worry about that. But we're going to end up making diagrams that look more like these boxes on the right. So this is my 1s orbital right down here on the bottom. So I have to put 11 electrons somewhere. So the 1s orbital can fit 2 electrons. So I go 1, 2. I've shown 2 electrons of opposite spin. It's okay to pair these right away because there's nowhere else for them to go. The 1s orbital just has that one little spot. Then I'm going to go to my 2s orbital, according to my Christmas tree. I'm going to put 2 electrons there. So I did my 1s, then I did my 2s, now I go to 2p. Now 2p is where we have to worry about this. So our 2p orbital is where we have to remember to follow that pairing rule. So we're going to put our electrons in here. We've already used 4, so we got 8 more we have to distribute. So we're going to go 5, 6, 7, 8, 9, 10. Now after our p orbital, so we did our 2p, we go down here to our 3s. Just to count again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, we want to turn this into an actual readable little configuration. So what we're going to do, just to kind of make this a little bit more simple, let me get this out of here so we have some room. When we communicate these, we don't want to always have to draw this whole huge diagram. So we're going to write this as 1s2. We're writing normal number 1, normal letter s, and then a superscript 2. 2s2. 2p. Now, the reason that this is a 2 is because there's 2 there, 2 there, so we have a 2 there. So then 2p, 6, 3s1. And that's our quantum configuration for sodium. So that's a very official, high-level science, smarty-pants way to write this. Now, we talk about Bohr configurations a lot. If we break this down by principal energy level, what this shows us, 2 electrons in the first principal energy level, 8 in the second principal energy level, 1 in the third principal energy level. If you look at sodium's electron configuration, you're going to see that it agrees. So this will essentially get you the same thing as your Bohr configuration. It's just a little bit more detailed. I kind of did a nice fancy version of this on here with some nice, some nice little electrons so that you could take a look at it. But again, you get that nice configuration, that quantum configuration: 1s2, 2s2, 2p6, 3s1. So again, we at this point are going to not really worry about magnetic and quantum spin. The spin quantum number is really just us showing those electrons facing, those arrows facing in the different directions. But for your purposes, other than showing the arrows in the different directions, you don't need to worry about that. And this is just kind of another energy diagram that I had on here because it's kind of interesting to see that, energy flip-flop right there. So I'm going to give you a couple to try out on your own. Go ahead, pause the video, try each of these, and then check your answer. Just to walk you through this if you're struggling, there are 14 electrons. Remember to start with your Christmas tree diagram. Make sure you're looking at your Christmas tree diagram while you're doing this. We start with our 1s, 2 electrons there. Next, we're going to go to our 2s. 2 electrons there. Our 2p. So at this point, we've used 2, 4, 6, 8, 10 of our 14 electrons. We have 4 more to go. So next we'll go to our 3s. Now we've used 12 of our electrons. We have 2 more. And this is where that not pairing them up rule is kind of important, because our electrons are going to go like that. Now, when you write your quantum configuration, it doesn't matter, because you still end up with 3p2, but if you're looking at one of these diagrams, it actually does make a huge difference. Unpaired electrons are actually why we have things like magnetism. So the fact that you can have unpaired electrons like that is why iron acts as a magnet, but other metals do not. So now you're going to write your quantum configuration. Pause the video and make sure to write that out. So we have 1s2, 2, oops, I just want to skip my s, 2s2, 2p6, 3s2, 3p2. If you break this down into your Bohr configuration, just for the sake of comparison to everything else that we're doing, you get 2, 8, 4. And hopefully that's going to agree with what you see on your periodic table. Now, some things that are interesting that you should be able to answer is how many electrons remain unpaired? So meaning they're sitting on a little line without somebody spinning in the opposite direction. We got 2 unpaired electrons. We also want to look at how many valence electrons we have. So our valence shell is our highest energy level that we're using, which is the third energy level. So our third energy level right here, or right here, contains 4 valence electrons. Oops, another silicone, sorry. So next I want you to try calcium. Pause the video for just a moment and do your diagram for calcium. Remember that you're following the Christmas tree diagram the whole time that you are doing this. So hopefully your configuration diagram looks like this. This is going to translate into 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So what's interesting about this example, I purposely gave it to you so you would see that energy situation that you get into where, you know, we're jumping, rather than going to the 3D, we're jumping to the 4s. So that's really important. You should not have had any electrons over here in this 3D because it's actually a higher energy level than the 4s. And this will work with our Bohr configuration if we break this down. Oops. So this gives us 2, 8, 8, 2. We want to look at how many electrons remain unpaired. We have 0 unpaired electrons. Our valence shell is our highest PEL, which is 4. And we have 2 valence electrons. And that totally agrees with everything that we would see using, using your Bohr configuration. So the last example for you to try is vanadium with 23 electrons. So you're going to have to make sure you use the Christmas tree. Pause it up, fill in your diagram. So once you got this diagram filled in, you had to go from the 3p to the 4s. Then you had a few more that went into that 3D, but it was important not to pair them quite yet. So you have 2 empty orbitals and then 3 unpaired electrons. So my quantum configuration for this one is going to work out to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. We do group those together even though they didn't really fill in that order. I know that's a little bit strange. And for s2. So look at our Bohr configuration, 2, 8, and then this one, sorry, took me a little minute there, 11, 2. What's really nice about this is if you look at your, if you look at vanadium's configuration on your periodic table, it's a weird configuration, but this diagram kind of explains that. In this diagram, we have 3 electrons remaining unpaired, and our 4th principal energy level gives us 2 valence electrons. So to wrap this up, there is a little shortcut. If you want to write if you have, for example, a quantum configuration, so nickel, for example, has this quantum configuration. You look this up and you're like, oh, the Bohr configuration would be a little bit easier to write. So maybe you want to write that instead, and you really wish there was a shortcut. So this is the noble gas configuration shortcut that we're going to talk about next really quickly. You select the previous noble gas, so the previous element from group 18, and then you fill in the remaining stuff based on, or the remaining electrons, I should say, after that noble gas. So you put your finger on nickel and then go to the noble gas before that. So you have to backtrack till you get to argon. Argon being our previous noble gas, sorry, this should say argon, not krypton. Argon has 18 electrons. So our first 18 electrons, we can actually, I'm sorry, I'm going to stop this here and make a separate video because this is